For our next presentation, we have Dr. Yannick Moy of AdaCore, one of the 2022 workshop sponsors, presenting dynamic memory management with ownership in Rust and Spark. Thank you to AdaCore for your continued sponsorship of the workshop. And now, Dr. Moy, it's all yours.
Thank you. So I'm going to present the ownership approach in two programming languages, Rust and Spark. This dynamic memory management is a new technique to approach dynamic memory management that we hope can be used in critical embedded software in the future. This also answers the concern and the query of previous attendees of the flight software workshop, which expressed an interest in a comparison of Rust and Spark. So this talk answers this need. The material for this talk was prepared with the colleagues from AdaCore, as well as Florian Gilcher from Ferrous Systems, in order to avoid being biased toward one or the other technological solution. Next slide, please. So memory fits in three buckets in applications. You have static data, which is known to the compiler and never deallocated. You have the stack, which comes in frames, which are pushed and popped down the stack when invoking functions in the application. And so here, allocation and deallocation are done automatically as the stack is pushed and popped. And finally, you have the heap, where allocation and deallocation are much more flexible. And we're interested in two sets of properties for the allocation and deallocation of this memory. We're interested in availability and correctness. So availability is the fact that allocation always succeeds, and correctness is the fact that the application behaves as if the allocation was never done. And as the colors here suggest, this is rather easy for static data, doable for the stack, and maybe quite difficult for the heap. So for static data, the data is known to the compiler and never deallocated, so it's easy to make sure it's available and correct. For the stack, the availability can be done through tools which measure the maximum stack size. And languages like Rust and Spark can make sure that there's no pointer that outlives the memory to which it's pointing to in the stack frame. So that's doable. The difficulty lies with the heap, where it's much more difficult to make sure that there's always enough memory available, in particular due to fragmentation of the memory. So is there enough contiguous memory that is available? For the correctness, when the deallocation is done manually, it's quite difficult to make sure this is correct. When it's done automatically with the help of a garbage collector, the memory management infrastructure is much more complex to deal with that and possibly very hard to certify. Next slide, please. So in 2011, the current avionics standard for software development was issued, so DO 178C. And with it came a supplement for object-oriented technology and related technique supplements. So this DO 332 document, which identified 7 risks and mapped them to 5 known techniques for dynamic memory management. Of the 7 risks, 3 were focusing on availability. So risk B related to fragmentation starvation, so the fact that there's enough contiguous memory available. Risk C related to deallocation starvation, so the fact that memory is leaked instead of being deallocated. Risk D related to heap memory exhaustion, so the fact that there's enough heap memory for the application at any given time. And 4 risks were related to correctness. So risk A, ambiguous references, relates to the fact that there are no unforeseen aliases to memory. Risk E, premature deallocation, deals with the fact that memory is not deallocated while it's still in use. Risk F, lost updates and stale reference, is particularly applicable to garbage collection, which moves memory. And finally, risk G, time-bound allocation and deallocation, is especially acute for the use of garbage collection, but other techniques need to take care of it too. And so the 5 techniques that were described were object pooling, where allocation and deallocation deals with objects of the same size to avoid fragmentation. Stack allocation, scope allocation, which is some evolution from stack allocation, And finally, a manual heap allocation, where the allocation is done by the application code. So you can think of the solution in C++, for example. And finally, automatic heap allocation, where garbage collection takes care of doing the deallocation like you would have in Java. Next slide, please. And you find this table in the DO332 documents, which does this mapping, which allocates the responsibility for dealing with risks to either the application code, AC, or the memory management infrastructure, MMI, for each of the techniques. Next slide. Yeah, so we are going to focus on these two, manual heap allocation and automatic heap allocation, which are the most flexible and which are, as you can see, on the extreme sides of the spectrum. In manual heap allocation, all the responsibility for these risks is assigned to the application code, at the exception of risk G, so time-bound allocation and deallocation. So the time that it would take to do a malloc or free in C code, for example. And on the automatic heap allocation, it's the contrary. All the responsibilities are assigned to the memory management infrastructure. So you could think of the garbage collector in Java, except for RISD. Heap memory exhaustion, which lies with the application code. Next. And because all these risks are assigned to the memory management infrastructure, which must deal with them in the most general case, that's also the most complex case to certify. Next slide. So we're going to describe here a new approach, the ownership approach, which was not present in 2011 when this document was issued and has appeared since then. Next slide. And we're going to start with Rust, because Rust has popularized this notion of ownership for, in particular, memory management. And ownership is really the key argument in Rust for both memory and thread safety. Every object in Rust has what we call an owner, which has all the rights to the object, so the read, write, and free rights to the object. And aliasing is strictly controlled. So when you assign a value, you're moving the value, that is, you're changing the owner of the value. The owner can still grant read and write access, and that's what we call borrows when there's only the read access, or mutable borrows when there's the read-write access. But the owner is the only one which can deallocate the object, and in fact, the allocation is inserted automatically by the compiler at the end of the lifetime of the owner. And so in the end, the correction of the application code with respect to memory and thread safety depends only on the safety of library abstractions in Rust that implements basic concepts of allocation and deallocation, like so-called box, ref cell, which deal with this automatic deallocation of owners. And these libraries indeed are implemented with so-called unsafe codes, which doesn't respect the same rules. Next slide. So let's see an example of ownership in Rust. So we have here a message which is exchanged between two tasks. So you can see at the top, there's a message which is just an array of bytes. And we create a sender and a receiver through this channel library. Then the task one creates a message and sends it to the sender. While in task two, the receiver receives the message, does something like prints it, and here explicitly frees the memory, so calls drop, although this call would be inserted by the compiler otherwise. So let's see the flows of ownership here in this code. Next. So the sender and receiver parts of the channel are moved to their respective tasks. So there's no duplication here. One is sent to task one and the other to task two. Next. And we can see the same occurs with the message. So the message is created in task one, moved to the sender, then implicitly moved to the receiver when the receiver receives it, and finally printed and dropped. And so there's always only one owner, which ensures the both memory and task safety here. Next. So let's see how this works in Spark. Spark is a subset of the Ada programming language targeted at program proof. So the ownership here is the key argument for being able to do proof on pointer programs. So it's every pointer object in Spark that has an owner, like in Rust, for reading, writing, and freeing the memory. So again, aliasing is tightly controlled. When you do an assignment between these objects, it moves the value, that is, it changes the order of the underlying memory. And again, we can grant a temporary read-write access through what we call observes and borrows, which mimic what you would find in Rust with the borrows and mutable borrows. The main difference here is that a Spark program is compiled with a regular Ada compiler, and so there's no automatic delocation of honors at the end of the lifetime. The delocation of the honor must be inserted in the application code, but the formal verification tool verifies that it's correct. So here, the correction of the application code depends on getting the code proved actually in the analyzer. Next. So let's see an example of exchanging messages between two parameters of a swap procedure here. So we have an array of bytes, which is the message. And we have this procedure swap with a contract, which says that in precondition, both messages are present, they are not null, and in postcondition that the content of the messages has been exchanged. And so let's see how this works next. So inside swap, these two parameters x and y are moved. So x is first moved to this temporary variable temp, which is then moved to y, while y is directly moved to x. So there's never aliasing here. Same at the caller side, when we look at allocating these messages, swapping them, and finally freeing the memory. Next. So we can see again that variables x and y are moved to the parameter swap. Here, the content is swapped. And finally, both of them are freed. And formal verification is going to ensure that this is all done correctly. Next. So we've seen different examples for Rust and Spark. Rust is focused on flight safety. So we saw an example which had tasks. And Spark is focused on program proof. So we saw an example with proof. But in fact, both examples can be written in both languages. So you can write a message exchange between tasks in Spark using a different syntax. So using what we call a protected object, which provides a mutex for the underlying memory to read-write the message through different tasks. So the proof will be able to show memory and flight safety, but it won't be able to reason about the specific sequencing of tasks. Likewise, the swap procedure can be written in Rust, and it can be specified and proved with various academic tools. So there's Crozo based on the Y3 technology. There's a Prusty based on the Viper technology, which have specification languages for Rust, which allow to write the same contract that we wrote in Spark and prove it on the Rust code. And so here, ownership provides the necessary basis for both memory and thread safety and proof of the pointer programs. Next. So we can go back to the table of DO332 and look at all the risks, A to G, with respect to the ownership approaches in Rust and Spark, and compare that to what we have for manual and automatic heap allocation. And so ownership in Rust only leaves to the application code properties related to availability, so the fragmentation starvation, risk B, and the heap memory exhaustion, risk B. And so it provides a new solution to dynamic memory allocation in critical software, which sits between the solution of manual heap allocation and automatic heap allocation, possibly a better solution for certification, as it leaves out this typical problem of availability to the application code, where it might be easier to certify. And so it decreases the complexity of the memory management infrastructure code. The solution in Spark is very similar, but instead of having these responsibilities for ambiguous references and delocation starvation and perimeter delocation allocated to the MMI, it's allocated to the application, but formally verified by the analysis tool. So with the same guarantees in the end. Next. So let's see now how this brings these languages and their ownership solution in terms of certification. Next. So starting with Rust, Rust so far has been largely used for mission critical software, lately in very large corporations like Amazon and Microsoft. But now there are people, companies interested in targeting safety critical software with Rust. And that's the goal of the project called Ferrocene between Ferrous Systems and AdaCore. Our goal here is to first qualify the Rust compiler toolchain for the automotive standard ISO 26262. But there are other domains which are interested. So you can look at the article Rust for Safe and Secure Avionics and Mission Critical Software, which was published last year in the Vertical Flight Society Forum by people from Collins Aerospace and Wind River. Next. So finally, Spark is used in most domains subject to certification. So in space, avionics, automotive, railway. So the main thing to remember, whether ownership is used or not, so pointers or not, is that when formal proof is used, it's not an all or nothing endeavor. In fact, there are levels of assurance that you can achieve, which come from the bottom level that we call stone of safer coding standard, to bronze with verification of initialization and data flows, to silver for absence of runtimers, which is typically the main goal targeted when people use Spark. And beyond that, it's possible to prove key integrity properties, whether they're related to safety or security or the functionality, up to platinum level, that is full functional requirements expressed as contracts and proved using the formal verification tools. And that's all. Thank you. Next. And I'm available for questions if there are any.
All right. Thank you, Yannick. We do have a few minutes for some questions. I see one just came in. But what do you see as the strengths and weaknesses of Rust and Spark relative to each other?
Well, so the main focus of Spark is obviously the formal verification, which Rust only has through academic tools right now. So that's one strength for Spark. And the main strength of Rust is that it's much more powerful in how it deals with ownership. So ownership is not only for memory management in Rust, it deals in fact with more generally resources. So you can deal with files, resources, and sockets, and all resources for which you want to maintain ownership. You can deal with that in Rust through the same concept.
Okay. And we have another question coming from a current panelist. What is the main adoption hurdle for Rust in the safety critical community?
So today it's certification. So that's what we have identified with Ferrous Systems. And so that's why we're working with them towards certification of the compiler and necessary core libraries. That's a big hurdle. And so that will require time to get it to the various domains where people may enjoy it.
Okay. And next question is, where does the Ferrocene project currently stand? When does that project expect to achieve certification?
So Ferrocene initially in the announcement of Ferrous Systems was targeting end of 2022. So today we are partnering with them and we're not committing to this very short deadline, but in the years to come, yes. That's what we aim for in the automotive domain.
Okay. Give a few more seconds for any other questions to come in. We do have a break up next, so we could start that a little early, but want to make sure that all the questions get asked. Another one just came in. Could you give some more background on how the memory management issues you profiled are typically managed currently in safety critical systems that are built on either C or C++ languages or languages with garbage collection? Are there any notable case studies on issues resulting from memory management issues that would be resolved by using a language with ownership like Rust?
I think the main question is the cost of certification. So today, dynamic memory management at the highest level of certification is not used because it's very costly to certify at level A of the 0178 garbage collector or user code that does dynamic allocation and delocation. So just the possibility of doing it is what ownership brings, in my opinion, because it brings a sweet spot in assigning responsibilities, like I showed, between the application code and the memory management infrastructure, and so separating out the availability parts towards the application code and the correctness part towards the memory management infrastructure or formal verification.
Okay. Let's see. Are there any other questions? All right. Thank you, Dr. Moy. I think we'll start our next break just a little bit early.
Thank you.